For years, a significant number of racers have been running alternative fuels. Historically, the most popular has been alcohol, which in the automotive context typically refers to methanol. Methanol has been used by USAC, IRL, Champ Car, and NHRI top alcohol class racers through the years. It burns with a clear flame with minimal subproduction and is very corrosive in its liquid form. Methanol is available from several sources, such as Sunoco Racing Fuels, VP Racing Fuels, and Torco. Methanol is a relatively simple molecule that starts out looking like methane, CH4, but replaces one of the hydrogen legs with an O group that now qualifies it as an actual alcohol to chemists. Because the fuel carries some amount of oxygen within it, the stoichiometric balance for clean combustion in air is shifted. If methanol were to be burned at the same mass ratio of 14.64 to 1 as most gasoline blends, there would just be too many oxygen molecules available for each hydrogen and carbon in the mix. The result would be a lean burn with less than optimal power. To fix this, more fuel is added per unit of air in order to achieve a balance of all hydrogens, carbons, and oxygens, which may come from either the air or the fuel itself during combustion. With methanol, this balance is a ratio of 6 to 1 in Earth's atmosphere. Methanol contains slightly less energy per unit, but because the stoichiometric ratio is so rich, relatively speaking, of course, more total fuel is burned on each cycle with the same amount of airflow. Once the correct ratio of fuel is delivered, the loss of specific energy per unit volume becomes irrelevant, as more total energy can be released with methanol than with gasoline for the same air mass. The limiting factor on how much power most engines can deliver is usually their maximum airflow limit. A limit on maximum airflow with a given target air/fuel ratio means a limit on total fuel delivery without going excessively rich and hurting power. If there is a limited amount of chemical energy to be released from the fuel, this also limits the potential mechanical energy out of the engine. With alcohol fuels that run at much richer mixtures in order to achieve the same chemical balance between hydrogens, carbons, and oxygens, more total fuel can be burned with the same amount of outside air being pumped through the engine. As long as the fuel system is able to keep up with the higher flow rate demands of an alcohol-based system, more total power can be delivered even though the specific energy of the fuel may be slightly lower. Alcohol fuels also tend to burn at a noticeably lower temperature than gasoline. This can greatly reduce loads on the cooling system, thermal concerns within the exhaust system at high power. Making large amounts of power from an engine with a fixed pumping capability gets easier when the fuel itself is helping to deliver oxygen to the cylinders. A 6 to 1 ratio of air and fuel looks pretty rich at first glance. Keep in mind that this is actually the balance point. If burned at that ratio, the chemistry does not see it as richer than gasoline that is being burned at 14.64 to 1. Rather, it's just a smaller molecule that happens to be contributing to the oxygen source of the air during the reaction. A ratio of 9 to 1 may be extremely rich with gasoline, but with methanol, it's exceptionally lean. To make things more clear, let's go back to using units of lambda. Lambda is just the excess air ratio for combustion. It does not care what type of fuel is being burned because it is really a reference of where things are at the moment compared to whatever the chemical balance point is. Equation 3.1 gave us the definition of lambda. In the case of alcohol blends as fuels, the stoichiometric air/fuel ratio is just different than what we're used to seeing for gasoline. Using methanol's stoichiometric balance point of 6 to 1, lambda can be calculated in much the same manner as with gasoline. If the actual ratio of 9 to 1 from our earlier example is to be observed in units of lambda, we find that the current excess air ratio is actually. The resulting lambda of 1.50 is so lean that combustion may not occur at all due to being near the lean ignition limit of the fuel, depending upon conditions. To get a clean burn, much more fuel is required. In this case, 50% more fuel would be necessary just to get back to the chemically ideal balance that is desirable at idle and cruise in most engines. Oxygen sensors and alcohol lambda sensors, both wideband or narrowband, do not know what type of fuel is being burned in the cylinders. Frankly, they don't care, and neither should you. What they tell you is which side of the chemical balance the engine is on at any given point. With a wideband, you just have the added benefit of knowing how far on either side of the balance the engine is. Although this may sound like a bit of a handicap at first, it's really a blessing in disguise. Remember that the oxygen sensor is really only measuring oxygen content and not fuel content in the exhaust gases. The display that is returned for air/fuel ratio on many cheaper units is really just lambda multiplied by about 14.64 to give the less educated user something he is used to seeing. If methanol is being burned at a ratio of 6.00 to 1 in an engine, the wideband sensor will detect a ratio of lambda equals 1.00. The cheaper units will display this as 1.00x 14.64 for an indicated ratio of 14.64 to 1. Obviously, there is a mismatch here. The problem arises from the assumption that the engine is burning gasoline when, in fact, it's really burning methanol. The wideband sensor is actually doing its job perfectly. It's just that the display configuration is misleading. The best course of action is to configure the display to only show lambda. That way, the calibrator is not confused by the conversion factor. Most experienced calibrators are used to working in units of lambda anyway, so there is no problem with stopping here. If you really want to see an actual air/fuel ratio with methanol, the wideband output configuration must be modified to show lambda multiplied by the stoichiometric balance point of 6.00 to 1. Once you can get used to looking at units of lambda rather than air/fuel ratio, it becomes far easier to tune almost any alternative fuel blend. Calibration setup for alcohol. So how does one set an EFI system up to properly control a methanol-fueled engine? The answer is surprisingly simple. All that's really needed is to open the target air/fuel ratio table and input new targets based upon the chemistry of the fuel being used. With methanol, most of zones 1, 2, 3, 4, 5, and 7 are set to lambda, I00, which is a ratio of in this case. When tuning the VE table, just look at the wideband output in units of lambda, not air/fuel ratio. Lambda will show the exact error if the target is stoichiometric operation, so corrections to the VE surface can be made based upon lambda alone. Make corrections to the VE table in the same exact manner as with gasoline by using the delivered lambda as a correction factor. When the time comes for WOT tuning with alcohol fuels, just keep working in units of lambda. The same lambda set points can be used with alcohol fuels as with gasoline. A naturally aspirated engine can be run at lambda, E87. With alcohol, just like gasoline, the only difference will be the actual commanded air/fuel ratio. If the base fuel map does not support units of lambda, simply calculate the desired ratio using a variant of equation 3.1 as before. The target air/fuel ratio within zone 6 can be populated with a ratio of 5.16 to 1 for use with methanol. This provides a safe starting point from which the WOT volumetric efficiencies can be calculated. Because alcohol fuels burn cooler, it may be found that this much extra enrichment is not necessary. Running slightly leaner, closer to LBT, around lambda 0.92 may be possible without damage on alcohol-fueled engines. Only actual testing of the engine in question with a loaded dyno or at the track will tell if this approach is acceptable. Alcohol-based fuels also have inherently high octane ratings. This high octane rating means that the fuel is not very likely to experience knock under higher loads and temperatures. Many alcohol engines will be able to run ignition angles all the way up to MBT timing at WOT without knock. Keep this in mind as testing is performed. Air/fuel ratios should still be corrected before optimizing ignition angle. Once the delivered air/fuel ratio matches the target, timing sweeps can be done to find the best power and torque for the engine. Don't wait for spark knock to tell you when too much timing has been delivered, as this may be well past MBT with alcohol. Just watch the torque output as timing is added. If delivered torque drops with added timing, chances are that MBT timing has been passed. Backing off the timing may actually deliver more torque output. Even in boost, timing may still be able to reach MBT with alcohol without knock. Don't be afraid of what looks like large timing numbers CAM paired to gasoline, but be careful not to go too far and lose power. Always try to run the minimum amount of ignition lead necessary to deliver maximum torque without knock or abnormal combustion contributes to the warming of the earth, so many efforts have been made to reduce the overall generation of it. By blending conventional gasoline with a percentage of ethanol, the carbon content of the fuel is reduced, which in turn reduces production of CO2 by the vehicles burning this fuel. Much like methanol, ethanol starts out as a simple hydrocarbon molecule. In this case, the base molecule would be ethane, C2H6, which is a 2-carbon chain. To make ethane into its alcohol equivalent, ethanol, and OH group again replaces one of the hydrogen atoms on the molecule. The result is another oxygen-bearing fuel that has a different stoichiometric combustion balance point that is somewhere between that of gasoline and methanol. The ethanol, one of the unintended benefits of the environmental movement, has been the availability of cheap race fuel. E85 is billed as a greener alternative to gasoline because its combustion results in lower CO2 production. Carbon dioxide is a greenhouse gas that stoichiometric balance for clean combustion of pure ethanol is a mass ratio of 9.00 to 1. Ethanol itself has an inherently high octane rating due to the compact shape of the molecule. The octane rating of pure ethanol is approximately 129 RON, research octane number, the higher of the two MON, motoring octane number is the other. So, in a rare coincidence, the environmental movement has led to widespread availability of cheap, high-octane fuel. Many different blends of ethanol are available today. The blend between ethanol and gasoline in E85 results in a stoichiometric balance point of a 9.85 to 1 mass ratio. When tuning an E85 application, simply use 9.85 instead of the 14.64 used for gasoline or 6.00 used for methanol for zones 1, 2, 3, 4, 5, and 7. For a naturally aspirated engine looking to run at lambda equals 0.86 at DOT, the actual target ratio is found as before by. Remember that even though this looks like an extremely rich ratio at first glance, it's going to behave similar to a gasoline engine operating at about 12.6 to 1. Also remember that a cheaper wideband may actually display 12.6 at this ratio when it really is measuring lambda equals 0.86 and converting it to a gasoline-based display number. Pure ethanol is actually rare and usually only available as a research fuel with correspondingly high pricing. However, E85 has become far more common at gas stations today. E85 is typically a blend of 85% ethanol and 15% gasoline. Adding the 15% gasoline to the mixture greatly helps cold temperature evaporation rates and makes storage less of a concern for water absorption. Just stick with the lambda reading to avoid confusion during testing. E85 has an octane rating of approximately 105, R plus M/2, depending on the blend. This high octane rating is what makes this green fuel attractive for many racing applications. In winter months, the fuel sold as E85 is usually actually closer to E70, a 70% blend of ethanol that contains more gasoline. This is done to aid in cold starting of the engine, since the alcohol fuels have lower vapor pressures than their gasoline equivalent and have trouble evaporating completely at low temperatures. During the transition months, the fuel in the tanks at gas stations selling E85 may vary anywhere between these two blends, so it's important to know what you're burning before getting too far into the calibration exercises. The blend between ethanol and gasoline in E85 results in a stoichiometric balance point of a 9.85 to 1 mass ratio. When tuning an E85 application, simply use 9.85 instead of the 14.64 used for gasoline or 6.00 used for methanol for zones 1, 2, 3, 4, 5, and 7. For a naturally aspirated engine looking to run at lambda equals 0.86 at WOT, the actual target ratio is found as before by. Remember that even though this looks like an extremely rich ratio at first glance, it's going to behave similar to a gasoline engine operating at about 12.6 to 1. Also remember that a cheaper wideband may actually display 12.6 at this ratio when it really is measuring lambda equals 0.86 and converting it to a gasoline-based display number. Just stick with the lambda reading to avoid confusion during testing. E85 has an octane rating of approximately 105 R plus M/2 depending on the blend. This high octane rating is what makes this green fuel attractive for many racing applications. In winter months, the fuel sold as E85 is usually actually closer to E70, a 70% blend of ethanol that contains more gasoline. This is done to aid in cold starting of the engine, since the alcohol fuels have lower vapor pressures than their gasoline equivalent and have trouble evaporating completely at low temperatures. During the transition months, the fuel in the tanks at gas stations selling E85 may vary anywhere between these two blends, so it's important to know what you're burning before getting too far into the calibration exercises. One such example is GM's Flex Fuel Sensor, used in some truck applications. This sensor returns a PWM signal to the ECU that indicates both alcohol concentration percentage and fuel temperature. If the ECU has the software to adjust fueling based on this input, it can make tuning with various blends of alcohol fuels a breeze. Two primary hardware concerns must be addressed when running alcohol fuels: capacity and corrosion. Because these fuels require larger volumes of flow to reach their stoichiometric and power enrichment ratios, the fuel system must be sized to support these higher flow rates. It takes about 5% more fuel volume to support the same air/fuel ratio with E85 as it would gasoline. This means that the fuel pump, lines, filters, rails, and injectors all need to be sized accordingly. Most OEM vehicles that are designated as flex fuel vehicles have the ability to detect the difference between the seasonal blends of ethanol-based fuels and normal gasoline. This is done either by a specific sensor or by a more complex logic within the ECU. The logic-based systems employ a virtual sensor that solves for alcohol content by examining fuel trims and knocks sensor feed back immediately after startup if the fuel level has changed. The logic used here is pretty involved and closely guarded by the manufacturers who have invented it, so it should not be expected to show up in the garden variety standalone controller anytime soon. The fuel composition sensor is typically installed either in the fuel tank or on the fuel feed line leading to the engine and is active anytime the ECU is running. Before simply buying larger capacity components, it's also important to consider the materials used. Alcohol fuels can be corrosive to the parts in many older fuel systems. Rubber and EPDM seals can literally be dissolved by alcohols, and the deposits may clog filters and injectors. Vitin, Teflon, or another equivalent material should be used instead. Aluminum will oxidize in the presence of alcohols too, so stainless steel fittings, rails, and hard lines should be used whenever possible with alcohol fuels. One such example is GM's pump gas. Even those of you running standard pump gasoline are probably getting a mild alcohol blend. By law, most gas stations today are now allowed to sell blends of as much as 1% ethanol as gasoline. The ethanol is being used to displace the MTBE, methyl tert-butyl ether, which has its own environmental and health concerns. It used to be that stations were required to post a sticker on the pump declaring the alcohol content, but that's no longer happening. Some regions were quicker to adopt the maximum allowable ethanol content in the pump gasoline. In my travels and discussions with shop owners and calibrators across the country, I've found that almost every station can be assumed to be selling some alcohol blend unless stated otherwise. In most cases, this means assuming a blend of 10% ethanol. Any addition of alcohol blends to the gasoline will shift the stoichiometric balance point. The more oxygen carried by the fuel, the richer the stoichiometric point will be. Where E85 has a stoichiometric ratio of 9.85 to 1 EIO, most pump gas blends will balance at about 14.2 to 1. This means that tuning to an assumed pure gasoline composition with a stoichiometric point of 14.64 to 1 may include a 3% error before the engine is ever started. The wideband oxygen sensor will still typically display at lambda, I00, even though this is really an actual ratio of 14.2 to 1 with a 10% ethanol blend. 3% may not sound like much, and it really isn't, but the idea behind engine calibration is to get all variables as close to optimal as possible. Leaving a 3% error in the fuel's stoichiometric point just makes tuning the volumetric efficiency table, startup fuel, and transient fueling that much less accurate. It's a good idea to just adjust at the beginning before baking that error into every other calculation later on. The only trick with EIO gasoline blends is that they must be treated like normal gasoline for the purposes of spark tuning. The alcohol in the fuel is part of the cocktail of additives used to get the desired octane rating. In this case, 91 octane really is just 91 octane, so the same care must be taken to avoid knock at high loads with EIO blends as is typically done with conventional gasoline. In most cases, this means assuming a blend of 10% ethanol. Any addition of alcohol blends to the gasoline will shift the stoichiometric balance point. The more oxygen carried by the fuel, the richer the stoichiometric point will be. Where E85 has a stoichiometric ratio of 9.85 to 1 EIO, most pump gas blends will balance at about 14.2 to 1. This means that tuning to an assumed pure gasoline composition with a stoichiometric point of 14.64 to 1 may include a 3% error before the engine is ever started. The wideband oxygen sensor will still typically display at lambda, I00, even though this is really an actual ratio of 14.2 to 1 with a 10% ethanol blend.